Good afternoon and welcome to this webinar, Saving Money with Smart Data Center Design. This event, brought to you by Mission Critical, is sponsored by Eaton. I'm your moderator, Caroline Fritz, editor of Mission Critical magazine. Thanks for joining us. Today's presenters are Ed Spears, Product Marketing Manager in Eaton's Critical Power Solutions Division, and John Collins, Product Line Manager. Ed is a Product Marketing Manager in Eaton's Critical Power Solutions Division in Raleigh, North Carolina. A 35-year veteran of the power systems industry, Ed has experience in UPS systems testing, sales, applications engineering and training, as well as working in power quality engineering and marketing for telecommunications, data centers, cable television, and broadband public networks. He may be reached at edspears@eaton.com. John is based in Raleigh, North Carolina, and has more than 20 years of experience in the data center industry. He is currently Product Line Manager, responsible for large data center solutions. He joined Eaton as Global Segment Manager for data centers. Prior to Eaton, he worked at Schneider Electric and held various roles in sales management and product management, where he was responsible for various global product offerings relating to power generation, power quality, and power distribution. He is involved in many industry groups, including the Green Grid, 7x24 Exchange, and AFCOM. John received his Bachelor of Science in Electrical Engineering from the University of Rhode Island and is working on his MBA at NC State University. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. If you're unsure about what an icon does, hover over the icon with your mouse and a box will pop up that tells you the function. Please take our survey following the webinar by clicking on the survey icon. Next to the slides window, there's a blank questions box that allows you to type a question in the box and then hit the submit button to send it to us. Later in the live program, our presenters will address as many questions as possible. Today's event is being recorded and archived on missioncriticalmagazine.com. All registered participants will receive an email within 1 to 2 business days with a link to view a recording of this event. And now I'm excited to turn it over to today's first presenter, Ed Spears.
Hello, thanks to the folks at Mission Critical Magazine, and thanks all of you for joining. And today we want to talk about saving money in the data center design, and specifically about UPS architectures that can help you do that. So let's jump right into the information here. I think most people on the call recognize that finding the most efficient method of deploying redundancy is very important, whether it's an enterprise, a multi-tenant, or co-location type data center. The redundancy and the availability of the power and cooling systems to support the IT effort is extremely important, but they have to do it nowadays with an eye towards efficiency. Now, efficiency never trumps reliability and availability, but they have to have an eye toward cost when they're putting these types of systems together. So for a sound infrastructure development for your data center or your critical operation, we'd like for you to consider a design that allows great uptime and availability, but also the ability to grow as you go, to not over-provision on day one for capacity that you may never need or may not need in the form that you may have originally installed it. You know, most clients recognize that it's very difficult to know what they're going to need even next year or the year after next, much less 5 or 8 or 10 years down the road. So they really require the flexibility to start with only what they need and add to it in large or small chunks as necessary and when necessary, and only if necessary. So one way that we can suggest to help save money in this process is the use of what's called a UPS catcher system, also known as an isolated redundant UPS system. This type of system provides excellent levels of redundancy without the costs and the complexity that you might have when you do a conventional parallel UPS or a 2-in or dual bus architecture system. And again, the cost is one thing, which can be very significant for this type of redundancy, but also the complexity. We find, as our competitors do, that oftentimes the problem that may exist in a particular installation is often due to confusion on the part of the operator when they take an action where they're not sure what that action is going to do. So if the entire system and power flow can be simplified in such a way while still providing great redundancy, then that's a very good thing to be able to do. So let's take a look at what we call a smart catcher system, again, otherwise known as an isolated redundant UPS system. And this is the type of system that includes an unloaded spare UPS held in reserve, and its output feeds the primary UPSs or multiple UPSs through their bypass feed. So in other words, instead of a UPS transitioning to plain utility power for maintenance or on a failure, it actually uses the output of the catcher UPS. And traditionally, these type systems have been designed with either one catcher for one UPS or maybe at a maximum one catcher UPS supporting up to three primary UPSs. And that's a little bit restrictive, but due to the fixed controls and the lack of intelligent operation, that was about as big as that type of system could get. And in very large installations, that's not quite enough.
Yeah, Ed, and I guess I'll add something to that. This is John speaking, and one of the questions we get a lot from customers was, well, what was the origin of the catcher system? And really, it goes back to the early to mid '90s, where in the advent of companies trying to build redundancy into their data centers and in the creation of these redundant architectures that we see today, not all UPS manufacturers were capable of doing parallel operations that we've taken for granted, where we can synchronize the output inverters of different UPSs. And so for some of the UPS manufacturers that are a little bit behind in that capability, they worked with some of their consulting engineer customers to create this type of isolated redundant, which became known as smart catcher, to be able to have that reserve UPS feed the static bypass of a primary UPS. And that was really the origin of this type of design, and really goes back to the pre-first.com build-out in the 90s.
So that's correct, and this next slide shows the traditional way that a catcher system was done. On the right-hand side of the slide, you see three primary UPSs along the bottom of the chart there, UPS 1, UPS 2, and UPS 3. And then above that, you see the catcher UPS, and its output of that UPS feeds the bypass input of the three primary UPSs. So you can see if, for example, if UPS 2 were to develop a problem and needed to transfer to bypass power, when it did that, the catcher UPS would provide that bypass source along with conditioned power and battery backup. So it would provide that type of redundancy on the failure of any of the primary UPSs. And again, this is traditionally deployed in a one catcher per UPS or up to a one catcher per 3 UPS. So this way you get some redundancy without having to make, in this case, 3 separate parallel redundant systems. For example, if I wanted to do traditional N+1 UPS paralleling, I would need 2 UPSs to form what is currently UPS 1, so UPS 1 would have redundancy. I'd need another 2 UPSs to form UPS 2 and another pair to form UPS 3. That would be a total of 6 UPSs, half of which are basically not needed to support the critical load and normal operation, along with their batteries and maintenance contracts and floor space and PI switchgear and all those kind of things. So a catcher system, as you can see, provides a great level of redundancy, but only uses 4 UPSs in this case. So it can provide some significant savings. So it was very attractive to use this type of system. However, it did have some disadvantages. For example, it operated off of a single bypass feed. If that bypass feed disappeared, then that complicated the operation of the system. It was affordable, but it did have the potential for what's called stranded redundancy. In other words, if, let's just say, UPS 1 suffers a failure, then the catcher UPS would then often be dedicated to supporting UPS 1, which means that if UPS 2 or UPS 3 developed a subsequent problem, the catcher UPS says, hey, I'm busy, going to have to do something else. So you could strand some of the capacity by dedicating it to only one of the 3 UPSs at a time. So those kind of things in a system where we want to be as reliable as possible and as foolproof as possible, those kind of things were actually disadvantages. the traditional catcher system had a few other challenges as well. It did require some type of PLC or SCADA control, and in many cases was used, albeit successfully, with some downstream static switches for proper system operation and proper system switching when problems occurred. But that again increased the complexity, and the whole idea here is to try to do this kind of thing with a minimum of complexity, especially for the operator who has to understand what they're doing and what happens anytime they take an action on site. As we mentioned on the previous slide, if I have a traditional catcher system and I have more than one primary UPS fail, I do run a significant risk of overloading the catcher UPS. The catcher UPS is usually not, for example, 3 times the size of the primary UPS, so I have to be careful that I don't suffer a disaster scenario where multiple UPS failures would cause the catcher UPS to become overloaded and then it would transfer to bypass. So to avoid these kinds of issues, clients would find themselves over-provisioning or putting in more catcher UPS than they actually need, for example, and more battery than they actually need, which increases not only the upfront cost, but the maintenance cost and the total cost of ownership. And the whole idea here is try to avoid over-provisioning that you might see with a traditional parallel system or a 2N dual bus architecture. So let's see what some alternatives are.
And Ed, I'll just add one comment to that, in that, remember that UPSs typically operate most efficiently when they're close to full load, and there's been some adjustment to that over time as manufacturers realize that full load really isn't the optimal target. But that catcher UPS, the reserve UPS, when it's not being utilized, is at 0% load. So it's in the most, it's kind of like driving a car at a red light. When you're stopped at a traffic light, you're getting 0 miles to the gallon. Same situation there. When that reserve UPS doesn't have any load on it, it's operating in its most inefficient manner.
That's exactly right. And just as an example, a large unloaded UPS with 0% load on its output can easily draw 10 to even 20,000 watts every hour that it's online. So you don't want to hamper your system efficiency by deploying a system in this type of situation. And if you can make the catcher system optimally sized, you can help with that type of thing. So on the slide here, we offer some features that we'd like to see as an improvement to the traditional catcher type system. First of all, some built-in controls that will be redundant, and we'll call them the brain for the purposes of this discussion, but something that would allow the catchers to increase the number of primary UPSs that it can support to get where, for example, I might want to have one catcher instead of having it serve 3 primary UPSs maximum. I'd like to be able to take care of up to 10 primary UPSs. That would be a lot better usage of the upfront expense and floor space and maintenance and all those kind of things. So the brain of the catcher system could evaluate the power consumption of each of the primary units and decide which loads can be supported by the catcher at any instant. So there's a lot more flexibility here, where a problem with the UPS doesn't result in that UPS grabbing and basically taking away the catcher from the rest of the UPSs. There's some sharing that can be done. And by adding logic and redundancy to this decision-making process, we get some variable power path transitions and some automatic operation that takes the right action no matter what type of failure occurs. So let's look at the next slide and see what this type of system might look like. So I'm going to spend a few moments describing the drawing at the left of this slide, and hopefully you can see my cursor as we do this. In this case, we show a system where I have a catcher UPS that's rated at 500 kVA, and its output feeds breakers called CIB that are feeding the bypass input of each of the 4 primary UPSs. And CIB basically stands for catcher bypass. I also would connect through a different breaker my utility bypass, and that would be connected to, again, to the bypass input of each of the 4 primary UPSs through breakers labeled BIB, or bypass isolation breaker. And as you can see in normal mode, the BIB, the utility fed breakers, are all open, and those breakers that are being fed by the catcher UPS at 500 kVA are all closed. So all 4 of the primary UPSs are being fed bypass power by the catcher. And notice also that the UPSs have different amounts of load on them. They might be different size UPSs, but we're basically interested in how much load is each primary UPS supporting at any point in time. So UPS 1 supporting 200 kVA, same thing with UPS 2. UPSs 3 and 4 are each supporting 400 kVA, and remember the catcher is rated for a total of 500 kVA. We don't want to make it bigger than we have to. So what happens if we suffer a failure on UPS 1? Well, clearly, if that happens, the UPS 1 will transfer to its bypass via its static switch and will begin to draw energy from the catcher system. Now, normally in a traditional system, at this point, the catcher system is basically taken away from the rest of the primary UPSs. It's now dedicated to supporting the one failed UPS. But in this particular case, you can see that I have 300 kVA of capacity left over in my catcher system. It would be really nice for the system to be smart enough to know that if UPS 2 were to subsequently fail, I could still handle that with a catcher. On the other hand, if UPS 3 or UPS 4 were to subsequently fail, I would overload the catcher and I would want those UPSs to be fed from the utility. And that's exactly what happens. In the scenario that you see on this screen, if UPS 1 suffers a failure, the CIB breaker on UPS remains closed because the catcher has capacity to support it and its load, but the BIB breakers would automatically close on UPS 3 and 4, making sure that the utility bypass is available to those UPSs should they have a problem. So in this case, we show UPS 1 suffering a failure and, of course, supported by the catcher UPS. Let's look at what happens next. Basically, the smart catcher system is looking at the loads on the output of the UPSs and basically setting up what I'll informally call a club. In other words, UPS 1 and UPS 2, they're in the club right now because the catcher UPS can handle them. On the other hand, let's say that UPS 3 were to fail and UPSs 1 and 2 were still okay along with UPS 4. Then UPS 3 would be in the club and no one else would be because the catcher system's only rated at 500 kVA. So the breakers up above the UPSs, the CIB, the catcher input breakers and the bypass input breakers, automatically under redundant controls will operate to determine who is supported by the catcher up to and including the full capacity of the catcher, and thus who is supported by straight utility bypass. So as you can see, there's lots of different scenarios, and the user would like the flexibility to not have to have all the primary UPSs be the same size. They'd hate to, for example, have to have 4 500 kilowatt UPSs when what they really need is a 200 kilowatt, a 50 kilowatt, a 500 kilowatt, and a 1 megawatt, for example. So it would be much better to have some flexibility there. And keep in mind that the decision making is not based on the rating of the UPS, but based on the load that we sense on the output of each UPS. So we're looking and saying, where are the loads, how big are they, and who's going to be in the club to be supported by the catcher, and who is going to be supported by traditional bypass operation. So hopefully that drawing there helps clarify a little bit what's going on in the logic here. Okay, moving on to the next slide. Here we see a human-machine interface, or an HMI, that helps make all of this possible. As I mentioned before, the controls that we're talking about here are redundant, and if all the controls, both redundant and primary, were to disappear for some reason, then the system is set up to automatically default to traditional bypass operation, so everything would stay online and would continue to operate. But this HMI system, here's just an example where a one-line drawing with actual controls is placed on a small box that can be mounted on the wall in the equipment room or in a monitoring station, a guard station, someone's office, etc. So they can constantly see what the status is and how the smart catcher is working and who has available backup and who's on standard bypass, etc. And that can be done at the small screen level. And again, can be placed literally anywhere that monitoring and, if necessary, control needs to be deployed. If we look at the next slide here, we see a little bit more elaborate system here. It's been covered up a little bit by the text, but this shows both the primary UPS and, in this case, about five primary UPSs and one catcher. So, but the idea here is to describe the benefits of the smart catcher. It depicts the system status operation via a graphical interface. It's easy to see what the power flow is and who's online and who's on bypass and who's being supported by the catcher or not. quick one-screen drawing here without having to follow a lot of lines to be able to tell what the status of the system is and what the capacity is going forward. It also supports expansion of the system over time by deferring capital and limiting maintenance costs to just what's needed. In other words, if on day one I need a 100 kilowatt and a 500 kilowatt UPS, I can go ahead and put them in and install a whatever size catcher I choose. But then I may not know what I'm going to need next. It may be a 300 kilowatt. It may be a 400 kilowatt UPS. It may be a 20 kilowatt UPS. Doesn't matter. The Smart Catcher system can accommodate any size UPS as long as the catcher system is bigger than the largest single UPS. So this provides the maximum operational flexibility since the UPSs don't need to be the same capacity, and by the way, they don't have to receive their input from a common source. I may have several input sources in a facility, and the UPSs, as I've deployed them over time, may be getting their input from different places. Catcher system doesn't mind. It can operate successfully regardless of where those sources are. So these kind of things allow the more typical type of growth pattern that we see where the growth is not planned to the nth degree 10 years out. It's a hodgepodge of additions and moves and changes and different requirements and changing loads and virtualization and all those kind of things. We need a system that can flex very easily and without forcing the client to over-provision at any point along the way. It also eliminates the need for downstream dual-source static transfer switches. If you're familiar with catcher systems, you know that those are frequently deployed, and while they do the job, it does add a significant amount to the upfront cost, and it's not just the upfront cost for the static switch equipment. There's also the real estate typically on the data center floor and maintenance and repair costs for those devices. Basically, it's a good idea to reduce the dependence on any switch if at all possible. That doesn't mean there's not fast switching involved in a smart catcher system, but we use the internal static switches that are built into every UPS to provide this kind of thing. And as we said before, we talked about a little bit towards the beginning of the presentation, it allows me to reduce the UPS hardware that I have to deploy. For example, if I want an N+1 redundant system at, let's say, 500 kW, then that would mean traditionally that I buy two 500 kilowatt UPSs, and each one might have, let's say, 4 refrigerator-sized battery cabinets that weigh 5,000 pounds each. So that's 8 battery cabinets, 2 UPSs. I'll need switchgear to tie them together in parallel. And I need to think about floor space and upfront cost and maintenance for the batteries and maintenance for the 2 UPSs. The costs add up on day one, and the total cost of ownership adds significantly just to get the desired, if not required, N+1 redundancy. That's a traditional way it's been done, and as a UPS vendor, we're happy to sell you more capacity than you have to have. We'll do that all day long. But it is a significant cost to get that redundancy. Smart Catcher system, as you see in the bottom portion of the screen, where I have a catcher UPS here, if you can see my cursor, and it is providing the bypass source for 5 primary UPSs that do not have to be the same size. They don't have to be installed at the same time. I may be installing those primary UPSs on an as-needed basis, but the catcher is there to support and can flex to support even more UPSs of different sizes as necessary, and as you can see, it can all be shown if color graphics and even controls on a single screen that might be on the UPS system, it might be on the tie switch gear, it might be on the wall in a guard shack or a control room or a NOC, for example. And again, it can be just monitoring or monitoring and controls. And remember that the brains that handle this and make the decisions can also be redundant.
And so I'd like to add to that, Ed, in that keep in mind here that Ed's showing some examples of some actual customers that we've worked with, but the intent of this presentation is to objectively talk about the concept and what's available out there for people to consider. And so the examples we're using aren't the only considerations. And what I mean by that is it is possible that the reserve UPS could even be 2 UPSs in parallel feeding a much larger bank of UPSs that are acting as primary. So you could have here 5, 6, or 7 primary UPSs and maybe one reserve UPS, you're not comfortable with that, so you put two UPSs in parallel as the reserve. And then what happens is if there's a problem with one of those primary UPSs, it switches to its bypass. Now, as opposed to a regular UPS system, bypass typically means utility power, but here we're drawing UPS protected power from the reserve system. That's how the load is never exposed to utility. So I just wanted to remind everyone that the examples we're showing aren't the only type of configuration to do it. As a consulting engineer or a facilities engineer, there are a lot of liberties you can take. The main part of what enables all this, as Ed's talking about, is that programmable SCADA system. That's the brains of the whole operation, controlling how the breaker operates.
Absolutely. Let's take a look at another drawing of a smart catcher system. And this just reminds us that, as we mentioned a couple of times, that we don't want to over-provision. Our clients don't want to risk paying for infrastructure that they may not ever use. And they've gotten to the point where they're simply saying, we can't afford to do that anymore. I need to start with what I need on day one and be able to add to it in little pieces or big pieces as necessary. So one of the things that this picture shows us is a system where on day one they might have bought two different UPSs that are shown here in blue, but they knew they're going to expand, so they arranged their switchgear with compartments that allow them to rack in or add different size breakers and additional breakers down the road to feed the bypass and the catcher inputs of both the original UPSs and any subsequent UPSs that they need. But it's very hard to predict what they will need on day one. But you see, with this type of system, you can decide, okay, I'll have a certain size breaker in year two. Once year two arrives and I know what I need, I can populate it with the appropriate size breaker and put in a UPS here shown in red that's not any bigger than it has to be at that time. It might be a large UPS. It might be a very small UPS. Doesn't matter. They all work together in a smart catcher system. And then as I continue to grow, maybe I need the fourth UPS. Don't know how big it'll be, but it doesn't matter. I can choose the breaker size and install in my existing switchgear and choose the UPS size on an as-needed basis. And while we have this picture up on the screen, it's worth mentioning that the catcher UPS shown here in the far upper right could operate in a high efficiency mode like our energy saver system. And this would allow, if utility power conditions are good, for utility power to come straight through the catcher system. This means that the catcher system, or the catcher UPS itself, will operate extremely efficiently, less than 1% losses, 24/7, 365. It also means, let's consider a situation, for example, when a short circuit occurs on the output of one of the primary UPSs. So we basically have a fault condition here. And the primary UPS is going to react to that fault by quickly transferring to its bypass. And in this case, its bypass is the utility fed through the catcher system, so we have a much better chance of supplying the necessary instantaneous current to clear that downstream fault. Whereas if I took a UPS output and transferred it to simply another UPS inverter output, the ability of those two UPSs in series to clear the fault would be extremely limited. So flexibilities like that are going to be the hallmark of providing better availability and better fault tolerance for the client's final system as configured. Here's another shot of an installed example where you can see a little bit more clearly the primary UPSs. In this case, there's 5 of them, and the catcher UPS. And if you look where my cursor is along the right-hand edge of the screen, you see that not only are there buttons like metering and alarms and options and files and setup. This is all done in Windows, by the way. But you also see one for controls. So if the client does want to allow remote control of the system, some do, some don't, or they need it in certain places and they don't want it in others, then that capability can be used or not used depending on the client's philosophy. So a smart catcher system can be even more reliable than, for example, a parallel system where I have to think about things like synchronization, load sharing, and selective tripping on failures. This gives us a little bit of an enhanced redundancy and a simplicity of both layout and operation. A couple of things here. If further redundancy is desired, and most clients do, the controller, the brain that handles the decision making here, can be made redundant, and the harnessing and wiring can be redundant as well. If the entire control system, literally Elvis leaves the building, all the UPSs will automatically close their traditional bypass breakers, so they'll be fed with bypass power, and that will again happen automatically and will happen in the absence of any kind of control whatsoever. So this makes the UPS systems independently of any system control and any master system brain, which is strongly desired in the systems that we make. We don't want to depend on a single brain for anything in a highly redundant system like we're describing here. So, getting to a summarization here, a smart catcher with logic decision making can go a long way in providing flexible and reliable and expandable system that can deliver the highest availability in the market. But if you remember, the whole point of this presentation is to be able to provide this kind of system in a cost-effective manner. We're really talking about saving money. That's the whole point. And go back to the first slide and check. We want to be able to do this and be able to point to not only money that we save on day one by not having to deploy such a large number of UPSs, but total cost of ownership benefits from everything from floor space to cooling for the UPS room and for the power cost of more efficient designs and fewer UPSs. So one other way to help with the likelihood of saving money and also saving speed to deployment would be prefabricated systems. And the next slide shows you 3 examples of prefabricated systems that are available, and these can be used in a smart catcher system. The one on the left here is what we call our connected system, and you see that 2 large UPSs are actually bussed into the back of the switchgear in such a way that we do not have to deploy cable and conduit for the input and output and bypass for those 2 UPS systems. Between the UPSs and the switchgear, they literally plug in and bus together at the bus bar level, so it saves significantly on installation and deployment time. The centralized system is a skid-mounted UPS where the UPS system up to 500 kilowatts and batteries and, say, a maintenance bypass circuit are all built at the factory, and the interconnect wiring, both power and controls, are connected at the factory, tested at the factory, and the entire 500 kilowatt system with batteries and bypass arrives on site on a pallet. And I could deploy this, for example, in a smart catcher system and bring in only the UPS that I need and the sizes that I need, and everything arrives on a pallet that can be rolled around on site, dropped in by crane. Whatever you need to do, you get an entire UPS system in a package where the internal interconnection wiring has already been done. And then on the right-hand side, you see a containerized system, which we also offer, and you're probably already familiar with these types of systems. They've been around for almost a decade now. And in our particular case, we don't use these to deploy IT equipment. It's strictly for UPSs and battery, switchgear, automatic transfer switches for the generator, air conditioning to keep the cabinet cool, fire detection and suppression equipment, and monitoring and that type of stuff is all included in a power container, if you will, that we offer for larger products between 800 and 1100 kilowatts. And all these are available today, and all of these can be deployed in a catcher system like we saw. Okay, so that's the end of my part of the presentation, and we are definitely available to answer questions or provide a little further commentary for anyone who's interested.
Well, thanks, Ed and John, for a great presentation. Before we answer the questions you submitted, if you'd like to schedule an appointment with today's sponsor, click on the Schedule an Appointment button to have someone reach out to you. And now we'll have our presenters address some questions that were submitted throughout the program. First, what is the impact on testing and maintenance of emergency power sources in order to use the catcher system?
That's a very good point. If we have fewer UPSs to be deployed to deliver support for the same load, then that's going to directly subtract from the amount of time and the amount of cost that I need to do for commissioning. The power path possibilities are fewer in a catcher system, and of course you want to test all of those when you're doing commissioning testing, so that helps. In addition, every UPS with a battery as part of its commissioning needs to have that battery tested. So if we use fewer deployed UPSs to do the job, then that cuts the time taken to do all of those battery tests, discharges, and recharges, and subsequent battery testing. So those kind of things really do decrease the total time needed for commissioning. By how much? In sites where we've deployed this type of system, commissioning time has decreased from between 20 and 30%.
Do you need to be concerned with phase synchronization between the catcher UPS output to a primary UPS bypass input during an event?
Very good question. All the primary UPSs will be looking at the same catcher system for their synchronization source. So this is a process that takes place automatically in any UPS system. The primary UPSs will be programmed to synchronize to their bypass source, which in this case is the catcher. Now, if the catcher situation changes and the bypass feeder, the BIB breaker closes and utility power then appears at the bypass input, those UPSs will synchronize to that. But regardless of the condition or regardless of the operating mode, there will always be a way for the primary UPSs to switch to a backup source, and they will synchronize automatically to that backup source.
The primary UPS system then has a rectifier feed, normal bypass feed, and a catcher bypass feed?
That's correct. The catcher bypass feed and the normal bypass feed, think of them as being tied together. So I have a bypass input to the UPS, and it is fed by either the bypass from the catcher or the bypass from the utility. So only one of those two breakers will be closed at any point in time. Either BIB will be open and CIB will be closed, or BIB will be closed, and by definition, CIB would be open. So only one source feeds the UPS's bypass under any condition.
How is the power passed through the failed UPS-1 when it has failed?
So when UPS-1 fails, the first thing that happens is the static switch inside UPS-1 will gate on and effectively transfer that UPS to its bypass source, be it the catcher UPS or utility bypass. And of course, the question I think here is that, okay, so I need to work on UPS-1 and do it safely, and I don't want to disrupt the critical load. So as with every large UPS that we sell or market, we strongly recommend the use of a wraparound or maintenance bypass circuit. So each of the primary UPSs would have a traditional wraparound bypass or maintenance bypass, otherwise known as maintenance bypass. I did not try to put that in the drawing just for simplicity purposes, but that would allow me to continue to feed catcher power to the critical load while I completely de-energize primary UPS number 1. Everything in that UPS is completely electrically dead and can be serviced and replaced. In fact, the entire UPS could be replaced if necessary without disrupting power to the critical load.
How does the catcher system make the decision regarding which primary UPSs can be supported?
That's a good question as well, and it's a question we get very often because it seems, intuitive that, okay, I look at the rating of those downstream UPSs and decide what to do with the catcher. But what actually happens is we look at the load on those downstream UPSs. So in the example that we had in the slide, we had two 400 kilowatt UPSs and two 200 kilowatt UPSs, all supported by a 500 kilowatt catcher. So that catcher is looking at the output load of each of those UPSs. So if one of the large UPSs was only loaded to 100 kW, then that 100 kW would be logged into the catcher system decision maker as there's 100 kW of capacity. So for example, in that scenario, I could have a failure on UPS number 1 that puts 200 kW on the catcher. I could suffer a failure then in UPS number 2 that puts another 200 kW on the catcher, and the logic then looks and sees, do I have anything out there that has 100 kilowatts or less on it? Yes, I do. Then UPS number 3 in that example would then be allowed to go to the catcher. here. So what it's doing is looking at the different loads on the different UPSs and saying, what combination of these can I support without overloading myself?
Yeah, and that's a great point, Ed. I don't want it to be lost on the answer is that the catcher system, the control system, you want your control system to look at the actual load of the UPS, not what the UPS is rated at, because we all know that UPSs are typically never fully loaded, especially in a redundant system. And so by looking at the actual load, you'll be able to have more of the primaries able to be backed up in the event of an emergency.
Exactly.
What if the one smart catcher brain breaks?
Good question again. Traditionally, our clients have used a redundant brain. In other words, the controls for the catcher system can be made redundant, and their wiring can also be redundant. It's really up to the user. They may choose to have just one brain, or they may choose to have two redundant brains. If all of the brains disappear, like we said earlier, if Elvis leaves the building, the system will automatically close all of the bypass input breakers to all the primary UPSs, so they will still have utility bypass to transfer to in the event of a failure. So even a complete loss of controls or redundant controls will not preclude the system from operating successfully to protect a critical load.
Yeah, and in fact, Ed, I guess a way to simplify that answer is if the brains of the system fail, it just reverts to operating as the same old catcher system we've known over the years that doesn't typically have any intelligence built into it.
Is the commissioning test different? Does it take longer to test all scenarios?
I think the total number of scenarios here can get large if I have, for example, 8 or 10 primary UPSs. But if I contrast that with the amount of commissioning necessary for an alternative like a dual bus architecture, I still think that the commissioning test, the total time needed for commissioning test, is going to be less for the catcher.
What about brands? Can units be from different brands?
Well, the technical answer to that question is probably yes. My commercial answer to that question is no, because we spent a lot of time developing this. So the reality is we're open to anything, and it's all about flexibility. But at the moment, we're offering this only for combinations of Eaton UPSs.
Can the UPS modules be normal UPS systems? It appears the control is the only custom device.
That's right. They can be standard off-the-shelf UPS systems. They don't need anything special to be able to be utilized this way. The feeder breakers, the CIBs and BIBs, they're in a separate piece of switchgear that is not inside the UPS. So yes, any primary UPS could be, in other words, a customer could redeploy one from building C to building B and say, well, I want to put that as part of the smart catcher system over in building B. All he has to do is transport it over there and hook it up and it'll work.
In the example diagram, was the 200 kVA unit and the 400 kVA unit in an AB redundancy? If not, was the equipment downstream single corded?
That's true. We're assuming here that each UPS has a separate output and is dedicated to a separate section of the critical load. But it's quite common to see folks that want to do either A, B at the distribution level or at the UPS level. And I think that adds a little bit of complexity to the controls, but it's not out of the question. In other words, if they said, I want the two 200s to be a part of an A-B system, then that's at least a possibility as well.
CIB and BIB breakers must be electrically operated breakers?
Definitely. So these would be motor-operated breakers. Other than that, they wouldn't be anything special, but they need to be able to operate by remote control.
Let's see. A question here, it says, I have a doubt. Can I get a rating IV with this proposal? The catcher UPS can fail while supporting any UPS out of service, and maybe the risk of blackout goes up.
So I think that question is referring to, and I'm guessing here, an Uptime Institute or a TIA type Tier 3 or Tier 4 rating that when it's about rating the system as fault tolerant or concurrently maintainable. And so the answer to that is, I guess, to be clear, to keep Eaton out of trouble, we're not in the business of certifying to the tier standards. We don't want to get in trouble with the Uptime Institute. But I would say, based on the design that we showed earlier, at a minimum, you're going to be concurrently maintainable. And then, I guess it would be up to the Uptime Institute judges if they would claim that it's also that Tier 4 fault tolerant.
How does the catcher shed load if primary UPS loads increase above catcher rating?
So what happens if the system says, hey, I've got more loads than the catcher can support? Then the UPSs that are currently supporting the excess load are going to automatically see their bypass input breakers close and their catcher input breakers open. So basically we're saying you guys that are excess here can still be fed by utility bypass, but the catcher doesn't have room for you. Remember, I was using the term back in the presentation about who's in the club and who's not in the club. If you're not in the club, that's not to say you don't have a bypass. You do, but it's utility bypass. And then if the load levels change, let's say tomorrow you don't have as much load on the other primary UPSs, next thing you know, one of those excess UPSs may find itself back in the club. And what that means is its its catcher input breaker would close and its bypass isolation breaker would open. So the controls take care of that automatically. They're constantly looking and say who has how much load, and let's adjust the bypass feed accordingly.
Is it necessary to have an interface between the control and the UPS?
Actually not. All we need to know is what's the load on the output of the UPS. So we could get that information from the UPS's internal sensing, but we could also get that information from, for example, downstream current transformers. So it doesn't necessarily have to talk to the UPS, but we do need to be able to sense what the output load is of each of the primary UPSs.
Could you explain again the scenario when one UPS transfers to bypass on a fault overload? How will the catcher handle it without tripping offline?
And I think I'm going to let Ed answer that, but I don't know if would it be easier to bring up that slide again? Do you think?
Yeah, it might be, and I can do that right quick. Hold on. If everyone can still see the screen, I think the slide we were using to describe that was this one here. Okay, and if there it comes. Okay, so let's use this picture here. In a traditional catcher system, where the catcher system, the catcher UPS is running in traditional double conversion operation, and its inverter output is feeding the bypass input of all the primary UPSs, and the primary UPS inverters are feeding the critical load. So let's take this last primary UPS on the right and say somebody drops a wrench inside a power distribution unit in the data center and shorts one phase to ground or two phases together. So basically I have a hard fault on the output. And at this point, we've created a little bit of a disaster scenario in terms of critical bus voltage going to zero. But what we need to do as quickly as possible is isolate that fault before the high current causes a fire, for example, or some other permanent damage to the installation. So in a traditional catcher system, the UPS which suffers the fault would immediately see an overload. It would go into current limit, and it would transfer to bypass on overload. But if that bypass was fed by yet another upstream UPS, in this case the catcher, well, that's another inverter there with a limited capacity for current, and it may not be able to clear the fault either, so that UPS becomes overloaded, transfers to bypass, and the utility finally clears the fault. That's a lot of things that need to happen in series. In the smart catcher system, it's not required, but we can recommend that we go ahead and operate the catcher system in energy saver mode with its static switch already conducting. That does two things. It saves us on a lot of quiescent power to keep that catcher UPS running, and it means that when I suffer a fault on any of the primary UPSs, I immediately, as soon as its static switch closes, I immediately have utility with its zillions of amps available to clear that downstream fault, whichever breaker or fuse is in series, and isolate that fault in the most expedient manner possible.
Is UPS distribution to the critical load single path?
It is single path in this case, but remember that you do have the ability to operate the primary UPSs as a dual bus architecture. In other words, I can pick two of them and say I want one of you to be side A and one to be side B. In that case, you would be out of the single path and back into the dual path. The client also has the ability, not to overcomplicate things, but they can take the path out of the UPS and then split it in two and do all the distribution from the UPS downstream as a dual path, even though they really only have one UPS supporting it. That's just an alternative.
Well, it looks like we're out of questions, and so that concludes today's webinar. Please join me in thanking Ed Spears and John Collins for their presentation, as well as our sponsor, Eaton. If you have any additional questions or comments, please don't hesitate to contact webinars@bmpmedia.com. As you exit today's webinar, please take a couple minutes to complete our survey. We strongly welcome your detailed comments to help us serve you better. Please visit webinars.missioncritical.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.